All right, welcome back to the Explainer. Today, we're diving straight into section 7.1, pitch, and we're going to completely redefine how we understand the science of sound. Usually when we talk about sound, we focus on the physics out there in the universe, vibrating objects, sound waves traveling through the air, acoustic energy, all of that. But today, we're shifting gears. We're looking inward at the human mind to tackle one of the absolute most fundamental auditory sensations we experience, pitch. By the end of this, you'll see that what you probably thought was just a basic physical property of a plucked guitar string is actually an incredibly complex, highly specialized illusion that is entirely generated by your brain. Pretty wild, right?
So here's our quick roadmap for today. First, we'll ask, what exactly is pitch? Then we'll break down pure tones and complex tones. And finally, we'll map out the existence region for pitch. Let's get right into it.
Section 1, what is pitch?
Let's kick things off by actually challenging the everyday language we use. Because technically speaking, something you probably say all the time is just flat out incorrect. Have you ever described a sound by saying, oh, it has a pitch of 100 hertz? Well, in the strict world of auditory science, that phrase is a total category mistake. Pitch and frequency are absolutely not the same thing. Frequency is the physical reality of the sound wave, right? It's the literal number of times a wave repeats per second, measured in hertz. You can objectively measure it with the machine. Pitch, on the other hand, is an internal, psychological sensation happening entirely in your mind. Think of it like this. An increase in acoustic intensity, which is literal physical energy, is experienced by us as an increase in the sensation of loudness. It's the exact same deal here. An increase in a sound's frequency is experienced by our brains as an increase in the sensation of pitch. One is out there in the physical world, and the other is quite literally all in your head.
Now, if you go looking for an official definition, the American National Standards Institute says that pitch is that attribute of auditory sensation in terms of which sounds may be ordered on a scale extending from low to high. But honestly, this definition isn't all that great. It's kind of too broad. Why? Because it forces us to strictly associate the words low and high with pitch. But think about it. We also use low and high to describe loudness, right? Like turning the volume high or low. So relying on those specific words just risks a ton of confusion when we're trying to be scientifically precise. Instead, let's adopt a much stricter, way more empirical test. Pitch is that aspect of auditory sensation whose variation is associated with musical melodies. I love this. It's such a brilliant way to frame it. Basically, if you take a sound, mess with its repetition rate, and you can play a recognizable musical melody, like, Happy Birthday or whatever, then you can be 100% absolutely sure that sound has a pitch. On the flip side, if varying a sound just sounds like random shifting noise and you literally can't make a melody out of it, it does not evoke a true pitch. We can call this the melody test.
Moving on to section 2, pure tones and complex tones.
To see how this actually builds into the real sounds we hear every day, we need to look at the acoustic building blocks our brains are using to extract this sensation. In auditory science, we generally divide our research into two main camps: pure tones and complex tones. A pure tone is the absolute simplest periodic waveform you can get. It's just a smooth, repeating sinusoidal wave, the fundamental building block of acoustics. A complex tone, on the other hand, is basically anything else that has a periodic, repeating waveform. These usually consist of a fundamental frequency plus a whole set of higher frequency components that we call harmonics, which are really just integer multiples of that fundamental frequency. Honestly, most of the sounds you hear out in the real world, from human speech vowels to a strummed guitar string, are complex tones. But here's the kicker. Under our new melody definition, both pure tones and complex tones qualify as pitch evokers. Why? Because you can use both of them to play a totally clear melody. Now, this next part perfectly captures the magic of human perception. Notice how the waveforms on the left side compare to their acoustic spectra over on the right. We're looking at 3 different sounds over time here. 1 pure tone up top, and 2 complex tones down below it. You can see how the shape of those squiggly lines gets way more jagged and complicated as you move down. Over on the right, we're seeing their acoustic spectra, meaning the actual physical frequencies contained in each of those sounds. That pure tone at the top, it just has one single lonely spike at 200 hertz. The middle one has spikes at 200, 400, 600, and 800. And the bottom one, it only has spikes starting way up at 1,000 hertz. Physically and acoustically, these 3 sounds are completely fundamentally different. But jump back to the left side for a second. The main repetition rate of all 3 of those waveforms is exactly the same, 200 hertz. And because of that shared repetition rate, your brain is going to hear all 3 of these incredibly different physical sounds as having the exact same pitch. It's wild. Pitch is simply the perceptual correlate of that waveform repetition rate. Which brings us to section 3, the existence region for pitch. So our brain's ability to group this information really brilliantly illustrates the mechanics of pitch. But if pitch is essentially our mind's, let's call it melody-making software, we have to ask a very practical question. What are the system requirements? What is the actual physical frequency range, what scientists call the existence region, where the software actually functions? I mean, our brains obviously can't translate every single repeating wave in the universe into a musical note, right? There have to be limits.
Let's start by looking at the absolute ceiling. Studies show that for pure tones and for complex tones that have a really strong first harmonic, the absolute highest fundamental frequency that can produce a recognizable melody is right around 4,000 to 5,000 hertz. If you try to play melodies using frequencies above 5,000 hertz, it just sounds completely bizarre. Like, you can tell the sound is changing, sure, but your brain literally cannot organize it into anything remotely musical. And it's actually no coincidence that classical music composers figured this out centuries ago just through trial and error. Think about the orchestral piccolo, the highest instrument in the orchestra. Its highest note sits perfectly right around 4,500 hertz. Makes perfect sense, right?
But hold on, because the rules change slightly for complex tones that are actually missing their first harmonic. Back in the 1960s, a researcher named Ritzma ran this incredible experiment using complex tones made of just 3 consecutive harmonics, and what he discovered was fascinating. He found that if your fundamental frequency is 100 hertz, you completely lose the sensation of pitch if you use harmonics higher than the 25th. But if you take that fundamental frequency and raise it to 500 hertz, that limit drops drastically down to around the 10th harmonic. So the big takeaway here is that it's a sliding scale. The higher the fundamental frequency of the sound, the lower the harmonic numbers need to be for your brain's melody software to successfully extract a pitch. Okay, so what about the other extreme? How low can we actually go? Well, for broadband complex tones, which just means sounds containing a really wide range of harmonics, starting from the first one and going up, the absolute floor for melody perception hits right around 30 hertz. If you go below that, the sound wave is repeating so slowly that our brain just stops hearing a continuous musical note. Instead, you start feeling this sort of vibrating rhythmic flutter. And once again, instrument makers found this limit totally naturally. Think about a standard grand piano. That lowest, deepest key rumbles at exactly 27.5 hertz, sitting perfectly right at the absolute threshold of human pitch perception. So, just to summarize the outer boundaries of this incredibly cool auditory illusion we've been discussing, the existence region for pitch is strictly bound. That sweet spot where repetitive sound waves are successfully perceived as musical pitch by the human mind extends purely from roughly 30 hertz on the very low end to roughly 5,000 hertz on the high end. And within that specific, relatively small window lies literally every symphony, every pop song, and every spoken melody you have ever heard and loved. So now that we've rigorously defined what pitch actually is, remember, it's an internal sensation, not a physical frequency, and we've mapped out its physical limits between 30 and 5,000 hertz, it leaves us with one massive lingering question. Exactly how do our neural pathways decode these specific repetition rates? I mean, do our auditory nerves just fire in perfect time with the wave, or do they map it by its actual physical location inside the inner ear? Well, that incredibly complex biological mystery is exactly what the rest of the science of sound is trying to unravel. It's an absolutely fascinating journey into neurobiology, but unfortunately, we'll have to save that deep dive for a future explainer.